I'm Chanyeok Jung from Dongguk University GTN Lab. The paper I will review technology opportunity analysis for creating innovative solutions, a framework for cross-field insight using patent data. Here is the bibliography information of the paper. The paper was registered in the Advanced Engineering Informatics in 2026. Table of contents is organized to match the structure of the paper. Introduction. Technological development is a key driver of competitiveness, and previous studies have viewed technological opportunities as expansions of functional possibilities. However, existing data-driven two-way approaches often focus on predefined domains and provide limited explanation of relationship among technologies, making it difficult to capture semantic connection across fields. To address this limitation, this study proposed a data-driven TOA framework that integrates recombinational search with a functional perspective using large-scale phantom data and future employs large language models to generate implementable R&D solution concepts that support particular problem solving and idea generation. The literature review. TOA plays an important role in enhancing innovation capability and competitiveness, and previous studies have proposed various approaches for capability building and technological forecasting. However, most existing methods remain confined to predefined domain and produce results that require substantial interpretation, limiting their practical usefulness. To address this limitation, this study proposed an analytical TOA framework that systemically extracts detailed technological information from domain related to a target technological problem. Many TOA studies use NLP to analyze large-scale phantom text, but most rely on back-of-word models such as LDA, which are limited in capturing semantic relationships. In contrast, path-based model incorporates contextual and semantic information, enabling more meaningful analysis. In particular, Phantom Spotter provides Phantom-specific sentence embeddings, and Partopic enables the extraction of interpretable, semantically coherent topics. Accordingly, this study adopts Phantom Spotter and Partopic as core method to integrate semantic text analysis into the proposed TOA framework. The methodology. As shown in Figure 1, the proposed methodology consists of 6 stages. Phantom data are collected and clustered using reference field and function from which core technological elements are extracted through semantic analysis, quantitative indicators, and network-based method. The resulting technological opportunities are validated using data-driven and expert-based approaches, and finally extended into evidence-linked, patent-aware solution concept using large language models. In the data collection stage, the target technology is defined based on the technological problem to be addressed. For example, for urban noise reduction is defined as the target technology and urban drones as the application domain. Patent data are then collected using both keyword-based searches in title and abstract and species classification criteria, resulting in a broad and systematic patent dataset. This stage, representative reference field and core function are identified using embedding mode-based semantic analysis and AO structure analysis. Patent abstract are embedded using Phantom Spotter, and Partopic is applied to cluster semantically similar patents. Reference fields are determined by selecting representative species classes based on combined frequency and semantic similarity score. Functions are extracted using action-object structure from patent title, abstract, and claims. After filtering and normalization, core functions are identified using a frequency and similarity-based scoring criterion. In this stage, patents are clustered to analyze how the function of the target technology are utilized across different technological domains. To achieve this, the previously extracted reference field and functional use as imperial knowledge and zero-shot topic modeling based on per topic is applied. This approach constructs cluster based on the semantic similarity between patent document and predefined labels, enabling a goal-oriented and interpretable analysis of how functions are applied across domains. In this stage, quantitative indicators are used to identify key patent cluster and to derive technological opportunities. Patent clusters are first evaluated by jointly considering technological value and technological relevance in order to identify clusters that are both technologically significant and well aligned with the target technology. Technological value is measured using patent family size and citation-based indicators, while technological relevance is assessed based on the semantic similarity between the target technology and each cluster. Based on this measure, key clusters are selected. For the selected cluster, technological novelty is additionally evaluated as a complementary indicator to distinguish exploitation-oriented opportunities from more exploration-oriented opportunities based on their similarity to existing knowledge. After identifying key cluster fine-grained technological information is extracted by sequentially identifying core reference build function, patent, and sentence. Reference builds are defined at the subclass level to capture more specific sub-technological domains. A co-occurrence network of species subclass and AO structure is constructed, and vector centrality is used to identify core reference build and functions with frequency used as a substitute when network construction is unreliable. Core patents are then identified by combining the centrality value of core reference build and functions as defined in equation 4, and sentences contain core AEO structure or extracted to derive technological insights directly related to the target technology. The study introduced an LLM-based concept generation stage to transform patent-driven technological opportunity into implementable R&D solution concepts. The LLM takes as input the target problem and application domain along with core reference build function and sentence, and generates solution concept by abstracting and reapplying online technological principles. The output or structure using a standardized schema covering the core innovation, technological feasible, and implementation pathway and are generated using the GPT-5 model. This is the result. Validate the effectiveness of the purpose framework. This study selects wearable device miniaturization as the target technology. Patent data were collected from the USPTO focusing on patent whose title, abstracts, or claims contain the term miniature and certify relevant species classification criteria. After removing duplicate record, a total of 9,342 patent fields up to 2023 were retained as the final dataset for analysis. Abstracts were first embedded using patent spotter, and pathofic-based clustering was then applied, resulting in a total of 10 clusters. The representative reference field of each cluster was evaluated at the species class level according to equation 1, and the results are summarized in table 2. As two clusters were identified as sharing the same reference field, a total of 9 reference fields were retained for the subsequent analysis. The structure were extracted from the title, abstract, and claims of the patent, resulting in an initial set of 10,387 AO structures. After applying similarity-based normalization, this number was reduced to 4,843 AO structures. The normalized AO structures were then evaluated according to equation 2, and considering interpretability, the top 8 AO structures were selected as the representative core function of the target technology. The results are presented in table 3. Zero-shot topic labels were constructed in the form of reference field function by combining 9 reference fields and 8 functions, resulting in a total of 72 labels. The zero-shot mean similarity parameter in pathofic was set to 0.145 to balance semantic coherence with for patent coverage. As a result, 6,860 out of 9,342 patents, corresponding to 73.4%, were assigned to 68 zero-shot topics, while unsigned topic and patent were excluded from subsequent analysis. The clustering results are illustrated in Figure 3. Each patent cluster technological value and technological relevance were calculated and visualized in a two-dimensional space as shown in Figure 4 to identify priority cluster for analysis. As a result, 22 clusters with high value on both dimensions were selected as key clusters. For future assessed technological novelty, 95 sentences containing the term wearable was used as background knowledge, and cluster sentence similarity distribution along with age-based weighting were applied. Finally, the characteristics of the key cluster were jointly compared across technological value, relevance, and novelty, and visualized using ladle chart as presented in Figure 5. Cluster with distinct reference field, functional focus, level of technological novelty, and patent volumes were selected for detailed case analysis. As shown in Table 4 and Figure 6, one cluster exhibited exploitation origin characteristic characterized by high citation-based impact and close proximity to existing technological capabilities. In contrast, the other cluster represented a more exploration-oriented opportunities, showing greater semantic distance from existing knowledge. Currently, as shown in Table 5 and 6, co-occurrence networks of species subclass and AO structure were constructed for each cluster, and in vectors, centrality was applied to identify the core reference field and core functions that represent each cluster. Combining the centrality value, patent level score were calculated, and core patent were identified as presented in Table 7. Finally, sentences containing the core AO structure were extracted from the core patent, enabling the derivation of sentence-level technological opportunities that are directly related to the target technology as shown in Table 8. To evaluate the reliability and practical usefulness of the purpose framework for data-driven and export-based validation approach or applied. For the data-driven validation, 7,872 patents filed up to 2016 were used as training data, while 52 wearable-related patents filed after 2017 were used as test data. As shown in Figure 7, 94.2% of the test patents were assigned to key clusters with high technological value and relevance, confirming that the proposed cluster evaluation and prioritization approach effectively identifies patents related to the target technology. Export-based validation was conducted with 3 industry and academic experts in the wearable and related field. The expert highlighted the framework ability to structure technological information around the reference field and function as well as its effectiveness in narrowing the analysis scope through the identification of core patent and core sentence. Overall, the export evaluation indicate that the proposed framework can serve as a particular support tool for addressing real-world technological challenges such as wearable device miniaturization. After validating the framework structure and instruction result, this study applied LLM-based solution concept generation to the key cluster semiconductor device, electric solid-state device that satisfy condition. As a result, multiple candidate R&D concepts were generated by integrating semiconductor manufacturing, flexible PCB, low temperature, collable ceramic composite, and wafer level memory embedding technologies as summarized in Table 9. The discussion. The study proposed a multi-layered TOA framework that structured technological opportunities from reference field and function down to the cluster patent and sentence levels. By combining semantic analysis with semi-supervised clustering, the framework enabled interpretable identification of synergies across heterogeneous technologies and future connects these opportunities to implementable R&D concept through the use of large language model. In the wearable miniaturization case, the framework was also applied to urban drone noise reduction and data center thermal management programs. In each case, highly relevant reference field and function were systematically identified. This result demonstrates that the proposed framework is not limited to a specific industry but can support cross-domain innovation across this diverse technological domain. While maintaining a patent-centered analysis, this study highlighting the extensibility of the proposed framework by allowing the selective integration of scientific publication of industrial report as supplementary signal when needed. In addition, recognizing that technological combination may raise legal and ethical concerns, the technological novelty indicator is used as an analytical tool to identify potential risk at the early stage. This is the conclusion. The study proposed a novel TOA framework that derived technological opportunities through function-based combinational search across multiple reference fields, addressing the limitation of existing TOA approaching in terms of restricted domain coverage and insufficient interpretability. Furthermore, by introducing an LLM-based R&D solution concept generation module grounded in the extracted opportunities, the framework contacts technology opportunity analysis with practical idea generation and problem solving. At the same time, limitations remain due to the reliance on patent-centered data and quantitative indicators, and future work should extend the framework through the integration of non-patent literature and additional validation effort. And Table 9 are included in the appendix to provide additional detail on the prompt configuration and the generated solution concept. This concludes my review. Thank you.